Okay, great! We'll start by loading the data from the NPZ file we saved in the last lecture. Let training data equal np load tfintro.npz. As you can guess, we could have skipped this step, but it's good to get used to loading your data from NPZs, as that's how you'll be usually provided with it. Okay. Next, we'll create two variables that measure the size of our inputs and outputs. The input size is 2, as there are two input variables, the x's and the z's we saw earlier. And the output size is 1, as there is only one output, y. All right. These two lines of code assign the values 2 and 1 to the variables input size and output size. That's programming you are already familiar with, so nothing new so far. Nota bene, because here comes the first difference. Unlike other packages where we have built-in models, when we are employing TensorFlow, we must actually build the model. So let's build our model. I'll store it in a variable called model. Model will be equal to tf Kira's sequential. Hold on, let's stop for a second. TF stands for TensorFlow. That's clear. What about Kira's? Well, as we have previously discussed, TF2 is based on Kira's, so that's the module needed. Finally, sequential is the function which indicates that we are laying down the model. It takes as arguments the different layers we'd like to include in our algorithm. While we haven't spoken about layers just yet, the algorithm we're building has a simple structure. It takes inputs, applies a single linear transformation, and provides outputs. These linear combinations together with the outputs constitute the so-called output layer. All right. You know from the minimal example with NumPy that the outputs are equal to the dot product of the inputs and weights plus the bias, right? In fact, there is another useful method here. It's called dense from TF Kira's layers. The dense method takes the provided inputs and calculates the dot product of the inputs and weights, and adds the bias. It is precisely what we wanted to achieve. Therefore, in brackets, we must simply specify the output size. We've already stored it in a variable, so we can parameterize our code by placing that variable as an argument. That alone is completely enough for our model specification. Great! Now, according to our theoretical framework, we need data, a model, an objective function, and an optimization algorithm. We've taken care of the data and the model, and are left with the latter two. The method which allows us to specify them is called compile. So, model.compile brackets. In the brackets, we include several different arguments. The optimizer, or the optimization algorithm, we will use is abbreviated as SGD. SGD stands for stochastic gradient descent, and is a generalization of the gradient descent concept we have already learned. We will dive into the differences later in the course, don't worry. To add it as an argument, we write optimizer equals quotation marks and the string name of the optimizer we want to use. Now, when using high-level packages that require a string, you'd want to check what you can actually include as a string. If we go online and check TF Kira's optimizers, we'll see a list of the names of different optimizers. This part of the documentation is where you can check the exact name of the optimizer we want to use. For this example, that would be SGD. Of course, we'll explore most other optimizers later in the course. Okay, the second argument we'll include is the loss function. We want to make this example as close as possible to our NumPy minimal example, so we have to use the L2 norm loss, scaled by the number of observations. In such cases, good theoretical preparation comes in handy. The L2 norm loss is also known as the least sum of squares. Moreover, scaling by the number of observations is equivalent to finding an average or a mean. Looking through the possible losses, we discover mean squared error. And mean squared error is precisely the L2 norm loss scaled by the number of observations. With that in mind, let's include the argument. Loss equal to mean squared error. Yep, it looks like we are done. We've loaded the data, outlined the model, and configured the learning process by selecting an objective function and an optimization algorithm. Well, almost. What we've got left is to indicate to the model which data to fit. Similar to many other libraries, TensorFlow 2 employs a fit method with two mandatory arguments, the inputs and the targets. Let's write model fit. In the brackets, we must specify the inputs that are contained in the inputs tensor from the variable training data and the targets, which are contained in the targets tensor from training data. Okay, this same method is also the place where we set the number of iterations. Each iteration over the full dataset in machine learning is called an epoch. So, from now on, we'll use this term to describe iterations and number of iterations. Now, let's set the number of epochs to 100. Finally, I'll set verbose to 0 and discuss it once we actually run the code. All right, in the next lecture, we'll look into the result. Thanks for watching.